Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 2 of Aero 3261's Structures 1. Today we're going to be covering some of the other effects that surround axial load, like deflections, thermal deflections, running loads, and things like that. Recalling back to what we covered last time when we looked at stress-strain curves, remember we saw that the slope of the stress-strain curve would just stress over strain. The slope of the load deflection curve is just force over deflection. This ties back to a concept we learned in physics where we found that the force, when you have a spring that's being deformed or lengthened, pulled on, that the deformation of the spring times the spring constant will give you the force. This is called Hooke's law. Now, while Hooke's law was originally developed for springs like F equals kx, it can be extended to materials, our stress-strain curve, by noting that the relationship between the stress and the strain is the modulus of elasticity. So since the slope of the curve, stress over strain, that's actually the modulus of elasticity that we're calling E. Now, while that usually when we use this value E, this modulus of elasticity, what we're actually doing, we're talking about the slope of the stress-strain curve in the elastic range. That's here where the stress-strain curve is straight. But actually the same relationship applies anywhere. It's just that the modulus will change. You can see the modulus, the slope of the stress-strain curve, is rather steep initially, and as you go around the knee it becomes flatter and flatter until at the fully plastic, when you get up to F to U, you have a completely flat modulus where lots of deflection with negligible change in stress, so your modulus eventually becomes zero. When we talk about the instantaneous modulus, or the modulus of elasticity at any point on the stress-strain curve, what we're really talking about is the tangent modulus, the modulus that's tangent to the stress-strain curve at any point. However, the number of the modulus of elasticity that we will usually use in aerospace will be that initial stress-strain, that initial modulus, which is the slope of the initial stress-strain curve. Every now and then we will go and use something that more approximates that tangent modulus, but most of the analysis will ignore the idea that for high stresses the modulus that we're using is completely wrong and just uses that initial modulus. Okay, so since we can write the modulus, we can write our stress-strain relationship using Hooke's law here. What that means is we can rearrange this and say, well, the strain is just the stress over the modulus, which is the stress over AE. This is going to set the groundwork for calculating our deflections on the next slide. So if we go back to an axial member being pulled on, like this particular material here, if we apply an axial load, it's going to deform with a deflection delta. We know that the strain is just a change in length over length. We also can write the strain from Hooke's law as the stress over the modulus, which means that's the P over A stress, that's the average stress, divided by the modulus P over AE. Now, since our strain is just the deflection over the original length, we can put these two equations together and solve for the deflections. We find this relation for the deflection. So far, we've learned a few key terms. The stress for an axial force, the average stress, is P over A. You should have that memorized. I'm not a huge fan of memorization for engineering classes, but there are certain equations that should be memorized. For example, there are many things that you don't choose to memorize, many pieces of news, but you probably know when your birthday is and what your name is. This is like one of those basic concepts. P over A for stress. For deflection under axial load, PL over AE. Okay? This is some of the things you're going to need. So if this is assuming that the force from one point to another, if that doesn't change, then you plug in the P for that length and the area, assuming the area doesn't change, and that the modulus in this range is all the same. If all those are the same, then you can just use one equation, PL over AE, to get the deflection. Now, if at any point along this, if let's say half of this bar were made out of one material and half out of another material, that would mean we'd have two E's, and we could just take the length of the first part of the bar and the length of the second part of the bar and the corresponding E, right, written as shown down here. For example, if this part of the bar is material 1, and this part of the bar is material 2, then our deflection, and let's call this L1 and this L2, then our deflection is just going to be the force times L1 over A1E1 plus the force times L2 over A2E2. It's that simple. If instead the area had changed, then we would have different areas here, and so on. If we have more pieces, 1, 2, 3, let's say this is material 1, this is material 2, and this is material 1 again, but with a different area, we would then have 3 terms. Does that make sense? These two, being different materials, would have different E, same area. These two being the same material would have the same E, but different areas. It's that simple. Now, this brings us to another idea. If you've ever pulled on something, as it gets longer, like let's say a rubber band, as you get longer, you'll notice it gets narrower. Okay? That actually is Poisson's effect. We're going to call it Poisson's ratio. So basically, if we pull on a rod like the one shown here, we know that the strain is just the stress over the modulus. That's one way of writing it. But that material, while it gets longer, it's also going to get smaller in the other two directions. Okay? What that means is if we pull a bar and it gets longer, the strain is just the change in length over length. If it also gets narrower, the strain in that other direction is the change in that length over its original length. So if this dimension was B and it now gets a little narrower to B prime, then actually that change in length, change in width over the original width is the strain in that direction. And if we pull on it, it's also getting smaller in the other direction. So the change in this dimension over its original dimension is the strain there. So we're going to get two negative strains under if we pull on this direction, get a positive strain here, these other two strains are going to be negative, even though there's no force applied in those directions. This brings us to Poisson's ratio, which we're going to define. We've got a nu here. The Greek character nu is often used. Also, you'll see in our handbook, it's called mu, right? So mu and nu are both commonly used for Poisson's ratio. This nu is more common. The reason I use mu in the appendix is because that's what's in MMPDS. So Poisson's ratio is defined as the lateral strain divided by the axial strain. That means the strain in the y direction divided by the strain in the strain in the other direction divided by the strain in the direction you're pulling. The strain in the other direction divided by the strain that you're pulling. Since the other strain was negative, Poisson's ratio is defined as negative. So a positive Poisson's ratio means if you stretch the member, it's going to get smaller in the other two directions. A negative Poisson's ratio means if you pull on the material, it gets fatter in the other two directions. There are very few materials that do that. Most of our materials are going to have a positive Poisson's ratio, which means that if you stretch it, the other two dimensions will shrink. Now later, when we look at more complicated stresses, we'll find if we have stresses in other directions, we'll have to account for the change in strain. Axial load provides a strain, and it also causes strain in the other two directions. If we have a stress and a force in the other direction, that will cause a strain in the other direction, and it will cause two corresponding shortenings in the two directions. We'll have to account for all those. We're not ready to do that, but that's coming up. Okay, so let's say we have a bar subjected to an axial force. We have two unloaded faces. That means two stresses are 0 and one is just P over A. Okay, so we can, this is another way of showing the same thing. We see that Poisson's ratio is just the negative of the strain in the y divided by the strain in the x. What this means is we can go and measure all these strains, measure these deflections if we're testing materials, and we can characterize our material that way. So we can write the strain in the x direction is the deflection in the x over the L. The deflection, the strain in the y direction is the change in width over the width in that direction, and so on. Got that? And therefore we can calculate the deflection in each of the directions. All we need to know is the one strain. If we have a single axial force like shown here, we can directly calculate the deflection in that direction, PL over AE, and we can use the strain from that in order to determine the changes in dimension in the other two directions. Now, if we have a statically indeterminate problem, now statically indeterminate, if you'll recall from statics, that means we have too many restraints to solve the problem by statics alone. In statics, we dealt mostly with statically determinate problems where we could just sum our forces and impose equilibrium and solve for everything. If we have too many constraints such that we can't solve it with statics alone, we'll then have to account for deflections. Now that we're in this class, we actually are learning how to calculate deflections, and we can use those to solve indeterminate problems. Now the way we're normally going to solve these was with a little trick. So let's say we have this part shown here. It looks like it's a member of 600 millimeters or 0.6 meters, right? And we can see we've got two different areas. Now in order to impose our deflection equation, PL over AE, we're going to need to break this up into pieces. If you look at this part, you see from A to D, we have one cross section and one force, whatever the force is in that part. Then because the 300 kilonewtons is applied, that next piece from D to C, although it has the same area and modulus, it has a different force. From C to K, we have the same force as we did from D to C, but we have a different area, so we need another term. And then from K to B, we have the same area, but a different force. We need another term. In order to solve this, we're going to have to systematically apply our equations of equilibrium. We'll normally use a little trick, and one of the tricks to do this would say, okay, if on the left here we have our applied loading, we can write it two ways. We can first say, okay, let's remove one of the constraints that over-constrained it, like the bottom constraint. If that were true, we'd have a reaction at A, we'd have a 300 kilonewton force and a 600 kilonewton force. We can now calculate the force in each piece. From K to B, there's no force in the member. Starting at the bottom, there's no force applied. So from K to B, there's no force. That means it's not going to deflect from there to there. From K to C, we have a force 600 kilonewtons. We have the area of 400 millimeters squared, which we're going to have to convert to meters squared. We have a certain modulus. And then from C to D, we have the same force, different area. From D to A, we now have 900 kilonewtons with the same area as C to D. So we got three terms. We can add those up and calculate the deflection of this piece under that loading. Got it? Now we're halfway done. Now, the part cannot deflect that way. So then we apply a force, a reaction force to the bottom. It's shown as RB. And we're going to use that force to eliminate that deflection. So the total deflection under this force RB is going to remove that deflection. So we can now take the deflection under that force. Well, if RB is applied, then the reaction at A for that force is going to also be RB. That means this entire part is now under RB under the second case. We're going to need two terms because we have two different areas. We're going to have RB, L of the CB over ACB E plus RB, L of the length AC over the area of that AC E. We can now set these two deflections equal to each other. Deflection that we calculated from the first part and the deflection that we calculated from the second part. Subtract the second from the first so that the total deflection ends up being 0 and solve. And solve it like this, sum these up, that gives us the answer. So this is how this looks on a problem. This is our problem. We idealized it this way. This is how we're going to address it. We just talked about all these per steps. We then can go ahead and show the math. Here's where we take our first sub case where this area 1, it has no axial load. 2 and 3 have the same axial load, and 4 has a different axial load. We have the area of the two pieces. We calculate our total deflection. Then we solve the second sub case like we discussed. under the action of RB. We then apply the two reactions, sum them together, and set that equal to 0. We then can calculate what the reaction is, and once we have the reaction, we can go and calculate how much force is in each piece. Got it? Makes sense? Okay. Here's another type of indeterminate problem. In this particular case, we have two members. They have the same length. They're different materials and different areas. So under the action of the force P, we see, okay, if we apply a force P, then we can calculate the deflection. The deflection is going to be the same in both materials. So we can calculate the deflection of the inner material and the deflection of the outer material. And those two deflections must be the same. And therefore we can solve this in the same manner. This is the deflection of the first material, the deflection of the second material. We can set those deflections equal and solve, and that allows us to calculate the individual forces in each piece. Does that make sense? Okay. This brings us to a new idea, and this is the idea of thermal strain. Now, when you have a temperature applied to a material, if you've ever sat in the bathtub, you'll notice as you sit in the bathtub, you tend to swell under the action of that as the moisture goes into your skin. And in the same way, when materials are exposed to temperature, they tend to swell. If you increase the temperature on the material, it will get bigger. If you decrease it, most materials we're going to deal with will get smaller. This is going to introduce us to the idea of thermal deflections. So let's just imagine we have a plate, as shown here, sitting on a frictionless surface, so there's nothing messing with our numbers. And let's say we apply a change in temperature delta T. If we change the temperature, it's actually going to get larger. If we just focus on this, now it's going to get larger in all directions. That means in this length, and the thickness. But let's just focus on the one dimension A to B, and we see it was L, and now it gets larger by some deflection, and we're calling it a thermal deflection for using a subscript T. Okay? Now, if we introduce the coefficient of thermal expansion, alpha, with units of inches per inch per degree Fahrenheit, then we can find that deflection is just alpha delta TL, and the strain is just alpha delta T. So we saw when we apply forces, the strain is just the stress. Since stress equals EE, the strain is just the stress over the modulus. And we can also write the change in length over length. For thermal strains, we find that the thermal strain is just alpha delta T. Whatever the coefficient of thermal expansion is for that material, multiplied by the change in temperature. It's not multiplied by the temperature, it's multiplied by the change in temperature. If you have a material here at, say, 77 degrees, then you go to Iceland and it's maybe 10 degrees or colder, that's going to cause a negative change in temperature, and that will cause it to shrink. If you take it out to the Sahara Desert, go up to maybe 200 degrees, then it's going to get larger. The strain is just alpha delta T, and the deflection is just the strain times the original length, or alpha delta T times L. Got it? Now, if we have this introduces us to a whole class of indeterminate problems for thermal problems. Let's say we have a part that's restrained at both ends and it's completely unloaded, but some idiot applies a temperature to the thing, a temperature change. Under the temperature change, this is going to try and expand. The new deflection it wants to go to is alpha delta TL. But because of the constraint, it cannot. Therefore, it develops a force to resist that, and that force causes a stress. So the way we can solve these is to remove the support, calculate the thermal deflection, and then apply a force that removes that. So just PL over AE that totally gets rid of that, and then solve for the force. That will tell us what the force is that develops at the reaction due to the thermal expansion. Okay, now this brings us to an interesting idea that I could have mentioned on the last slide. We know that the thermal strain then is alpha delta T, right? And we could also say it's the change in length over length. The stress, though, is for forces, it's EE, modulus times the strain. But if we have that piece, let's say that piece that we saw last slide, sitting on a frictionless surface, if we apply a delta T, it gets larger, but because nothing constrains it, it develops no force. It's very happy to get larger, just like you sitting in the bathtub, you're happy as a lark. If you get in the bathtub, even though you swell due to moisture absorption, you're happy. Unless, let's say you're in a bathtub that's too small, and when your body tries to swell, it now squeezes up against the bathtub. All of a sudden, you start getting irritated. You're getting caused stress. So, stresses are caused by forces, and they're caused when you constrain thermal members. But if a member expands thermally without constraint, there's no stress. So there's no stress associated with thermal strain, so Hooke's law doesn't really apply to thermal strains because you can have strains with no stress as long as you develop no force. So if we have, anytime we have a member with a delta T, if it's unrestrained, there will be no stress associated with the strain. It will strain, it will deflect, but it will not develop stress. If you constrain it so it cannot move like it wants to, that's when it develops stress. Got that? It's very critical you understand this. Now, when we get to composite materials, we have different materials with different coefficients of thermal expansion. Then the part is trying to do a bunch of different things under the same change in temperature. You can develop a lot of residual stresses due to those thermal effects. It can get rather complicated. We'll teach you all about that if you come back to take composite materials. Got it? Okay. We're going to introduce a new concept, and this is the idea of running loads. This is usually not covered at the undergraduate level, but I heard you folks were wanting to be aerospace engineers, and if you want to be an aerospace engineer, you really need to understand how to calculate running loads. Now, running load is just the force per unit inch. So let's say we have this force applied to a rod, right? The force is P. The stress is P over A. In this particular case, the area of this force is the area that's normal to the force. So actually the stress is P over BT, right? Now students that don't really understand that much will calculate P over BA. That's completely wrong because the area that's normal to the force is the one that's shown right here. That area is T times B. So the stress is P over B T. The running load, now this force actually, if you look at, well, how much force per inch, you could say, well, the force per inch on this thing, if we say this is the running load N, is just the force divided by this length. The running load is just the force divided by the length, which in this case is B. The stress associated with a running load is just N over T, because N is P over B, so that means it's P over BT. Okay? It's important that you understand running loads at this point because we're going to be using these ideas interchangeably. So once again, going back to our force, our running load is just P over B. That running load is shown like this. We'll often use N for this. If it's a shear running load, we'll often call it lowercase q. We'll look at that in a couple lectures. Okay, right now we're just looking at normal stresses or axial stresses. So that's just going to use that N subscript. So the force is just N times B, since the running load is just P over B. The stress then is just the force divided by the area, which is P over A, which is NB over BT, which is obviously just N over T. This idea of calculating the appropriate running load, N equals B over T, and the stress is N over T, and also that's equal to P over A, is critical that you understand at this point. Got that? Another idea, so strain energy. We talked about strain energy of axial forces last time. Remember, our energy is just the force times the deflection, right? We talked about that last time. And this energy then, force times deflection in the same direction. Now, it's the summation of that though. So actually, if you take the integral of f dx, if we're down in the elastic range, then actually the force deflection relationship is linear as is shown here. And since it's linear, the area under the curve of that integral is 1/2 p delta. So the energy, once again, the energy is the force times the change in length. But if that relationship is going up this curve as we see here, if it's going up this curve as we see here, then actually the area underneath this curve is just the area of this. If you take this integral, it just gives you 1/2 p delta. So often when we're talking about the energy, we're going to say that the energy is 1/2 of p delta. You're going to say, where did that 1/2 come from? I thought it was just force times deflection. Yes, that's true. But if we're in the elastic range, then actually the area under that curve, p delta, is just 1/2 p delta. Now, if we had, let's say we have something that as we apply it, like a spring, as we apply the force, it lengthens, but the force holds constant. Now the energy is just p delta. But if it's in the elastic range, then it's 1/2 p delta is the area under that curve. If we had a load deflection curve, p deflection, actually we saw that looks something like this. It's going to be something between these. It's whatever the area is under this. We'd have to integrate that puppy, right? But if we're talking about the elastic strain energy, we'll see this 1/2 p delta. We're just going to hurl a 1/2 at it. A lot of books will do that without really explaining it. And the reason for that is because they're talking the area under that curve and you're down the elastic range. Got that? So if we have axial forces, we can write our strain energy this way. Our change in force is the stress times the little increment of area. That means we can also write the deflection as the strain times the dimension, right? Since the change in length over length, that change in delta over dz, the original width, is just the strain. We can combine these ideas to write the equation for the strain energy, and we get this change in strain energy like this. We want the total strain energy in the entire part. We just sum those up, and we can write it this way. Since from Hooke's law, we see that the strain is just stress over E. Plug that in, and we find this relation. Now this is actually out of Hibbler. This is changing nomenclature. This N in this case is not running load. It's unfortunate we just introduced running load. Let's do this. So this, see, they're calling a force N, not P. So let's just change it. Let's just call this P. That means this is p squared, p squared. These are forces, not running loads. So the total strain energy, if we have a uniform cross section, is p squared L over 2AE. Got that? Now if we have a varying cross section, we would have to integrate that puppy. But if we have a constant cross section, we can just do this. Let's say we have a part like this with one area, and then it goes to a larger area. All we need to do to get the total strain energy, we calculate the strain energy for this length and then the strain energy for that length and just add those puppies together, and that'll be the total strain energy for the part. Got that? Okay, let's look at some example problems. So let's say we have this part here. This looks pretty straightforward. Let's say we want the deformation. How many elements do we need to break this up into? Actually, do you remember what the equation for deflection is? PL over AE. How many times do we have to apply that? Well, we look at this and we've got one force from A to B. So we need a section for that, length 12 inches. And then from B to C, we have the same area, different force. And then from C to D, we have a different force and a different area. So we're going to need three terms. We sum up those three deflections and those three pieces. That'll be the total deflection. This tells how we're going to do it. Blah, blah, blah. And if we look here, we see it done numerically. We got the length of each section shown, the area of each section calculated. We calculate the force in each member. From D to C, it's 30 kips. From C to B, it's 30 minus 45, so it's minus 15. And then from B to A, it's adding another 75. So that gives us up to, what, 60? Then we take our 3 pieces, we sum those puppies up as done here, and we get the total deflection. Pretty straightforward. Okay, this is a different problem. This is out of Beer and Johnson, and it's not necessarily intuitive. We haven't learned a lot of tools. Beer and Johnson usually likes to use a lot of problems that require you to have leaps of judgment that you may not have developed the experience for. In this particular case, we have this force 30 kilonewtons, and we're calling this bar BE rigid, which basically means it doesn't deflect under that transverse shear. You haven't learned how to calculate the deflection due to transverse shear yet. We'll do that later this semester, so that's fortunate. So what we're going to do is pretend that this BDE remains perfectly straight. What this means is all we need to do to figure out what the deflection of this is evaluate the axial deflection of the 2 rods at AB and CD. How do we do that? Well, first we're going to have to solve this statically. Since AB and CD are 2 force members, you'll notice there are 2 pins, and from statics we learned that's a 2 force member. That means we know that the force in those 2 members has to be axial. Has to be axial. It could be tension or compression. So we can sum our moments about point B. Just replace this AB with a force. We can just replace this length with the force. It looks to me like this force is going to be compressive, and this force is going to be tensile. We can draw a free body diagram of this member, sum our moments about point B, and calculate this reaction, P, from C to D. Then we can sum our vertical forces, and we can calculate this PAB. Once we have that, we can calculate, based on those forces, we can look at the deflection. The deflection of each of these is just going to be PL over AE, where P is the force in that member, L is the length of that member, A is the area of that member, and E is the E of that member. So we're going to get deflection here, and we're going to do deflection here, right? Actually, it's going to be more like this one's going to be moving up, and this can be moving down. Then, if we just, since this is rigid, we just attach those 2 points, and we can use trig, similar triangles, to calculate what this deflection is. That's what you're going to see in this solution procedure. This is not totally intuitive, and that's why I'm spilling all the beans about how this kind of problem is solved. Okay, here's our procedure, and here's the summation. They first draw a free body diagram as shown up here at upper left. They sum their moments about B, sum their moments about D. We could have summed our vertical forces for the second one. They look at the first member and calculate the deflection up here, and then they look at the second member and calculate deflection. They then are going to set those 2 deflections as shown here. We find that at B it moves to B prime, at D it moves to D prime, and since that member BDE is rigid, they just draw a straight line between those 2 points and use trig to solve what that deflection at that point E is. Got that? We saw this problem last time. We got a force. All we got to do is calculate the collective area, which means 4 times 0.2 plus the upper flange, 4 times 0.2, plus 5 minus 0.2 minus 0.2, looks like about 4.6, times the thickness of that piece, which looks like it's probably also 0.2. P over A, and that's our stress. Got it? That's all we got. Enjoy.